And as you can see, today we are going to revise this topic of today, relative velocity. So relative velocity, actually you can use the term relative motion, which includes all the term relative displacement, relative velocity, and relative acceleration. All are three related terms. So this is something what we are going to do today, relative motion. And moment we think of relative velocity. So just think of relative velocity. If we understand the vector sum and vector difference, that is enough to solve majority of the questions related to relative velocity. So it's very simple. It's just most cases finding vector sum or vector difference depending on what the case is. And it becomes vector sum and difference become even simpler if we express both in form of a unit vector Cartesian system. And what is relative velocity? I think entire relative velocity is based on one simple relationship. We call something like this VAB. What does VAB mean? VAB is velocity of A as seen by B. And what is VAB is equal to? We can write sometime VA minus VB, but we can also write as VAG. What is VAG? Velocity of A as seen in the ground frame minus velocity of B as seen in the ground frame, which is VA minus VB. So this is what I think this major part of the topic is understanding and application of this simple relationship. So when we write this here, when we write this expression, B is the observer. What does observer mean? So if we call B as an observer or B is the frame of reference, we have to imagine as if the coordinate system is attached to B. And when we are measuring VAB or the displacement of A, we need to find the position of A at any time t with B being the coordinate system. So if we understand that part, that is major part of understanding relative motion. And it becomes very simple. So we start with very simple understanding in terms of 1D, which we experience. See, relative motion we experience every day. Relative motion in 1D. So to understand relative motion in 1D, see in case of 1D, it becomes even simpler because even in case of one dimension, since only two directions are possible, 1D motion, only two directions are possible. So we can identify the direction in terms of plus or minus sign. Okay, so there are, say, suppose there are four different objects, and all objects, though they are shown as a Raja, we can just imagine all are represented by a dot. Okay, everything can be identified like a dot, and these are four objects here. And these are the time nature of motion. The person B is at rest. Car A is moving towards right 20 meters per second. Person C is walking towards right 4 meters per second. Car D is moving towards left with 10 meters per second. So in this case, when we talk about relative motion, see, motion is a property of observer and as well as object. So when we, in case of 1D, it is very simple to understand. If we talk about magnitude, here the directions, the magnitudes add up when velocities are in the opposite direction. So what does it mean? Suppose all four of them are in space. If they're in the space, if I write up something, what is the velocity of car D as seen by A? So what is velocity of car D as seen by A? If I take the positive velocity, it will be velocity of D minus velocity of A. I'm not putting the bar sign. One dimension, we can easily understand that part. So what is VD? VD, we just put the value. VD is equal to minus 10 and minus this is 20. So this comes minus 30. What does this indicate? If we look at car D, when both are in motion, whatever nature of motion A observes for D, if A was at rest and D was moving at the speed of 30 meters per second towards the observer, both have the same, it will give the same impression. So and second thing, so this is VDA to A, D will appear to be moving towards left with 30 meters per second. To B, car A will be moving towards right with 20 meters per second. To C, car A will be moving towards right with 16 meters per second. So where both are in the same direction, it will take the difference. To car D, A will appear to be moving towards right with 30 meters per second. They are in opposite direction, it will add up. And whatever VDA we get, VAD will be, so whatever velocity A observes for D, D will observe opposite velocity. So when object and observer interchange, the relative velocity also becomes inverse. And one more important point we can keep in mind. If a coordinate system is attached to say car A, if R A becomes the observer, it means coordinate system is attached to A. And if the coordinate system is attached to A, the observer car driver who's sitting in the car, he will always be at rest in that frame of reference. So moment we attach a frame of reference, moment we make something as observer, effectively it makes that object at rest. So any object in its own frame of reference is at rest. And so when assign a frame of reference to particular object, effectively that object becomes at rest. And that simplifies some questions. Okay, so we'll continue. So motion is a combined property, frame of reference and all. In case of dimension motion, we come across two common cases. What are the two common cases we come across? That's what we're going to do in the later part. When object moves on a moving surface. So its ground velocity is different. See, like a person is moving on a train. And that is a case, in that case, the person is walking on the surface of the train, which itself is moving. Person walking on escalator, person walking on travelator. And it's also the case, person walking in water. Person walking in water is called swimming. Boat, the way even the boat, if you row a boat in a flowing river, the river surface also is like a moving surface. If you see the river, you can see the plastic bottle, other objects floating, and those objects will be moving at velocity of same velocity of the river. So even river also is a moving surface. So when a boat or swimmer moves in the river, that also is equivalent to us in terms of conceptually. That case is similar to a person walking on a moving surface. So what is the purpose? The velocity of the man, we'll see it later. Velocity of the man is equal to velocity relative to the surface he's walking on plus the velocity of the surface. Okay. That's one case when observer moves on a moving surface, its ground velocity is different. That's one type of case we'll look at. And second common case is when observer is in motion, like raindrop. See, raindrop, how the rain is falling, it will appear different to different people depending on their motion. So if rain is truly falling vertical, we see it later. If the person really truly falling vertical, it will be seen vertical by a person at rest. But if a other person is walking towards right, to him it will be falling like this. And to a person who is walking towards left, it will be appear to be falling like this. So why it is appearing like this? Because here it is seen from a frame of reference which itself is under motion. So any question where observation is made by a person in motion, or observation is it is observed from frame of reference which is under motion, that is second category. So what we observe is not the ground velocity, what we observe is the relative velocity. So these are the two common cases we have to keep across. Even first case, one more example you can think of, a person walking inside the train, person walking on the deck of a ship which is in motion, person walking on travelator or escalator, boat moving in a flowing river, and also airplane moving in blowing wind. Even that also is example of object moving on a moving surface. In case of aeroplane, what is the moving surface? Even it moves on which surface the airplane moves on. If you have to at all think of the surface airplane moves on is air. And air itself will start moving, air itself will give you velocity. So there also make assumption if air is blowing, wind is blowing, if there was no friction, if there was not friction, not correct. Similar to we take the rain case, it would have moved the aeroplane with the same velocity as the wind velocity in ideal scenario. That's the assumption we make, though it may not be very realistic, but that's the assumption we use to solve the questions. Right. Okay. So let's see again, to understand this expression, we'll not go into derivation, but let's have a understanding where does it come from, just to get a feel where does this relationship comes from. So we'll take a simple example. So when we talk about position, when we say like something like this, typically when we say a person is moving at the speed of 4 meters per second. So unless we specify whatever motion we talk about, generally that motion is in ground frame of reference. What does ground frame of reference mean? In that case, it means the coordinate system or measurement is made from a point which is not moving with reference to ground, something like a pole. Okay, something which is at rest. So position is measured with respect to fixed point. Or it could be also person which is not in motion, when all displacement and related quantity are in the ground frame of reference. So let's take example. So we take 1D motion, this 1D motion, this is the direction in which all the motions are happening. It could be like a road. So it's a straight road, all motions are happening in the road. And this could be a fixed point, which is a pole. So there's an object A, it could be anything. So object A, initially at some time t, we make observation at 2 instances of time. So one instance of time, you find this position. Yes, we see this is a frame of reference. We can assign the position vector as plus xa, because this direction we have taken is positive, and plus minus sign is enough. And after time t, it moves to new position. So if I observe from this frame of reference, this was my initial position vector. This was my final position vector. Final position vector, my initial position vector becomes my displacement. So in this frame of reference, this is a displacement. So what is displacement? Xa prime minus xa. That's the displacement. Final position minus. So this you can easily understand what the displacement is. That's the displacement in fixed frame of reference. There's another object B, which is also under motion. So it moves from during the same time interval. When this A is here, B is here. When part A it moves to A dash, B also moves to B dash. This also has undergone displacement. And let's mark its position. So this position also xb and x prime b. So this is that the observation positions we have recorded, position of points we have recorded with reference to a fixed point. What if I want to make B itself as a frame of reference and observe motion of A? That becomes your moving frame of reference. So if this becomes coordinate system, this becomes my origin. If this is my coordinate system, what is the initial position of A? This distance is equal to initial position of A. So what is this distance equal to in ground frame? I can write this initial position in frame of B is equal to xa minus xb. So we can do the like initial position of A as observed by B is equal to xa minus xb. And what is the final position? Final position, the coordinate system has moved from here. But as far as B is concerned, this is the reference point. And what is the final position? Final position vector is this. This distance, positive distance, is the final position. What is this distance equal to? Xa prime minus xb prime. That's the final position. And what is displacement of A as seen by B? Final position mode vector minus initial position vector. If I subtract this from this, I get my displacement. But this displacement would be which frame of reference? In frame of reference as B. So when I subtract from this, I subtracted this from this, keeping negative sign, subtracted this from this. So this difference can be written like this. Because there's advantage of writing like this. What is the displacement of A with reference to B is equal to displacement of A in the ground frame minus the displacement of B in the ground frame. And if we divide this displacement by time, this becomes velocity of A in the ground frame minus the velocity of B in the ground frame. That's what this expression is. And we can do so. We have done in 1D. We can do in the y direction also. And we take the vector sum. It becomes a relationship in 2 dimensions. But what we have derived is valid for multiple dimensions also. So this is the understanding of how this expression is arrived at. Okay. Reference. Okay. Now let's apply it to some simple question in 1D. 1D is fairly simple. So all of you read through question and think in your mind. It's a very easy question to solve. And then I will go about solving this. It's a fairly simple question. Let's look at this. How do we evaluate this question? If you draw a figure, this is car A moving the speed of 60 kilometers per hour. It's followed by car B, and separation between them is 5 kilometers. I have not marked the distance. The distance is 5 kilometers. How is the truck moving? Truck is moving the opposite lane. We don't know what is velocity. Everything in kilometers per hour. So the truck is moving like this. So what we have drawn here, see, since we talk about the truck moving the opposite direction meets the 2 cars in a time interval of 3 minutes. How do I understand this term better? See, if right now it has met car A. So if truck person presses a stopwatch here, the moment it crosses the second car, by that the car would have moved somewhere, and truck also moved somewhere. The reading of the stopwatch when he crosses the second car would be 3 minutes. That's what time interval mean. So basically from this instance, the time taken for this car and this truck to meet is 3 minutes. So that is very simple. So time to cross successive car, how much time it will take for this car to reach here? See, if I observe from frame of reference of the truck, if I make the truck as a coordinate system here, okay, what will the velocity of the car? If I write what will be velocity of car B in the frame of reference of the truck will be equal to VB minus VT. VB is equal to 60 minus a truck velocity is minus V. It will be 60 plus V. And this is what we talk about when they move in the opposite direction. It gets added up. So time to take a truck successive car would is distance by speed, but we are talking about relative speed between truck and the car. And since it takes 5 minutes, 5 kilometers, and time is given, time is 3 minutes, we can arrive at the relative velocity. And relative velocity 5 kilometers in 3 minutes is equal to 100 kilometers per hour, 20 into 5. So relative velocity comes to 100 kilometers per hour. It means 60 plus V is equal to 100. It implies truck velocity is 40 kilometers per hour. Okay. So a similar question you can try and solve the other way around also. What is the other variation of the question? All of you, I will not do this question right now, but you can try that question. Other question we can solve. There's another fast moving car traveling in the same direction as car A and B, this car C, and this is a fast moving car. It takes successive car in time interval of 3 minutes. It overtakes in 3 minutes. What is the speed of this car? And that's another question you can solve. Pretty simple. So we understand both ways. Read the next question. This question we had done it before, but earlier we had done as two individual motions. This time we'll solve this question using relative velocity. So some of you might find relative velocity is much simpler to understand. So let's read the question here. You have seen it earlier. Bus starts from rest with an acceleration of 2 meters per second square. And many of you might have experienced, you want to travel a bus, you see the bus at a distance, and bus is just started. It could be train also. It starts with an acceleration of 2 meters per second square. And we assume the acceleration remains constant. Within that time period, we are talking about this question. So within the time interval, which is relevant here, is constant. So man is running at a constant speed. Man is running at a constant speed of 10 meters per second. Distance between them is x. It is x meter behind. What has to be maximum value of x so that man may be able to catch the bus? Okay. So to catch the bus means both must come to the same position at some real value of time. Then only it catches the bus. Let's observe. Let's see. Analyze this question. How this motion would appear in the frame of reference of the man. So just assume, see, this man is just like Arjun. He is only looking at the bus, nothing else is visible. How would the bus motion will appear to this man in this kind of scenario? Okay, so we are attaching frame of reference to the man, we attach coordinate system to the man, and then analyze how the problem would appear as viewed from man's frame of reference. When we made man as a frame of reference, coordinate system is attached here. When we attach coordinate system, so what is velocity of the bus? Velocity of the bus will be equal to VB minus VM. So in this frame of reference, let's redo this question in this frame of reference. So coordinate system attached to man, it is equal to man as at rest. He will only see things moving around him. How would bus appear to be moving to him? Let's first carry it out. So since we have taken man as a frame of reference, velocity of bus as seen from man will be equal to VB minus VM. And which comes to equal to, hence it become negative term. So bus will up at that particular time t is equal to 0. Bus will appear to be coming nearer to him at a speed of 10 meters per second, or distance between them will appear to be shrinking at 10 meters per second. And if you see relative acceleration, what will the acceleration of bus in the frame of reference of man? It will be equal to acceleration of bus minus acceleration of man. What is acceleration of bus? It is positive 2. Acceleration of man is 0. Hence, acceleration will be positive. So what does this mean here? We have seen this kind of motion before. This is something velocity and acceleration are in the opposite direction. So bus will seem to be approaching the man with a gradually reducing speed. And it will, in the as seen by my man, if he keeps looking at this keeps happening, it will keep appear to be approaching the man at a slower and slower speed, come to momentary rest, and then it will appear to be going away from him. This kind of motion will appear in the frame of reference of man. Okay, so in man's frame of reference, the bus will be coming towards him. Distance will keep decreasing with a gradually reducing velocity. Since there's an acceleration here, after 1 second, earlier it is appear to be approaching him 10 meter per second. After 1 second, the bus will appear to be approaching 208 meter per second at 2 seconds 6. So like this, speed of approach of bus will continuously keep on reducing because of this acceleration in the opposite direction until it appears at momentary rest, then appears to be moving away with the increasing speed. So what has to happen? We know in this case, when it moves like this, from this point, it will have a maximum displacement. What is the maximum displacement it has? U square by 2a. So this one from here, from initial distance of x, it will have a negative maximum displacement of u square by 2a. So maximum displacement we are towards the man will be u square by 2a. And if I substitute u square 100 by 2 into 2, 4, it is 25 meter. So in this frame of reference, the bus will move towards him by distance of 25 meter. If x is exactly equal to 25 meter, the bus will just, at a moment, he will just by the side of bus and the distance will keep on increasing. If x is greater than 25 meter, the bus will come to certain distance and move away. It will never meet the man. But if x is less than 25 meter, in that case, what will happen? If the bus motion will be, if you look at this, how would the bus move? Bus will appear like this. Distance will become 0. And if the man doesn't get into the bus, we are assuming the man keeps running at 10 meter per second. For some period, he will find the bus has gone behind him. What does it mean? Bus position negative. It means the man has overtaken the bus. But this the point again, at this instant, the bus speed becomes same, and then bus start moving faster, starts overtaking. So if a man keeps running at 10 meter per second, if this distance separation between them is less than 25 meter, in that case, man will overtake the bus. If he doesn't get into bus, keep running, he will overtake the bus. But after some time, since the bus is always speed is increasing, at some point of time, its increase will become equal to speed of the man, and then greater than speed of man, and bus will finally overtake. So that's how we can understand motion between two objects which are having velocity and acceleration. It is easier to solve using concept of relative velocity and relative acceleration. You can again go through and see this easy. Okay, so this is how it will analyze in one-dimensional motion. Let's take one more example of motion in 1D before we move on to 2D. This also just read through a question. Okay, lift having floor, and this kind of common question you can come across. You can experience this one. Read this through. And 2 seconds after start, bolt begins to fall from the ceiling. So what is happening? Up for 2 seconds, it is both bolt as well as lift. They have a constant acceleration of 2 meters per second square in the upward direction. And after 2 seconds, the bolt becomes loose and start falling. What is the time? What is the free fall time means? It is the time taken by the bolt to move from the ceiling to the floor. What is the time taken? This also, if you think of it, is a one-dimensional case. The lift also moving in vertical direction, bolt also moving in one direction motion. It involves two objects here, and we can solve this question also in a manner very similar to previous question if we can interpret question properly. So let's see how do we interpret this question, how do we solve this question. Okay, so what are the two objects which are of interest, which are relevant here? Two things here, which have to meet here. Bolt begins to fall. Free fall means what? What are the time we are talking about? Time ends. Time of free fall ends when the bolt hits the floor. So two objects which are relevant are bolt and the lift floor. Okay, so what will happen? So until 2 seconds, bolt also had an acceleration of 2 meters per second x square. Soon after, bolt becomes loose. That is time soon after this. What does time t is equal to 2 plus delta tt mean? Soon after bolt losing contact with the ceiling, bolt will have a downward acceleration of g. That's the point we need to understand. Soon after board losing contact with the ceiling. So this how figure we can draw. This is the what the figure would look like at time little after 2 seconds. Little after 2 seconds. Bolt has become loose. This distance is close to 0. So 2 seconds until this point, entire lift as well as bolt have acquired a velocity of 4 meters per second. The bolt also had a velocity of 4 meters per second at this time. The floor also has a velocity of 2 meters per second. Even after this interval, the floor will continue to have an upward acceleration of 2 meters per second square. But since bolt has become loose, it is no longer in contact with the ceiling of the lift, which was applying the force earlier. Earlier, it had an upward acceleration because ceiling, the point where bolt was attached to the ceiling of the lift, that point was exerting an upward force on the bolt so as to give an acceleration of 2 meters per second square. Moment becomes loose, only force acting on the bolt is gravitational force, and hence it will only have a gravitational acceleration. So this is a velocity and this is acceleration. It has an acceleration of 10 meters per second square. So this is one object, this is the second object. This is the distance between them, 2.7 meters. They have velocity of 4 meters per second, 4 meters per second, equal velocity at this instance because just become loose, but their accelerations are not equal. Okay, so these are two objects. Now we simplify. So till 2 seconds, the ceiling was exerting force on the bolt to give it upward acceleration. But as soon as the bolt gets loose, it will have downward acceleration of g. And we have to always keep in mind, as any object becomes loose from a moving object, at that instance, it will have same velocity as the object to which it was connected. So that's why both have same velocity. Okay. So in the frame of reference of the floor, so what we assume here, we attach the frame of reference to the floor. So either you can think of where are you? You assume that you are here. Just be like a tiny little ant if you are placed here. You are observing from here. How would the motion of bolt appear to you? Or you attach a coordinate system here. How would motion appear to you? So this we identified this is the frame of reference. So when we take this frame of reference, the motion also we need to take in ground velocity and acceleration. We need to convert it into relative velocity and relative acceleration. Relative velocity will be 0, both are equal. Relative acceleration, there in the opposite direction will add up. So in that case, in the frame of reference of the floor, bolt will have a downward acceleration of 10 to 12. That's what I have written here. BBF will be this value. So bolt will have a downward acceleration of 10 starting from rest. That's how the figure will look like. So in this frame of reference, if you are the observer here, tiny little ant sitting here, if you observe from this frame of reference, bolt will appear to be accelerating towards you with this acceleration of 12 meters per second square starting from rest. Initially, the velocity is 0. If this is acceleration, it's pretty simple to solve. How much time it will take to travel? So a bolt to come and strike this floor, it has to have a displacement of 2.7 meters. So we can easily write, so S is equal to 1 by 2. This frame into t square, we find t is equal to root of 9 by 20. So that's how we solve. I hope all have understood. Okay, now coming to object moving on a surface. Now we'll come to two-dimension motion. And one of the important things to understand in this part here, relative velocity, and this comes to swimming. So before I go to example of boat and river, which sometimes is not very intuitively easy to understand. What is little easier to understand is motion on the solid surface, which is solid surface could be what? Solid surface could be a road, which is at rest. Solid surface could be a travelator, which is moving in the constant speed. Solid surface could be also like a deck of a ship, or it could also be surface of a train. Okay, so let's take a simple case first, one dimension, and then we go to second dimension. So let's assume that this is a long train, and train is moving at the velocity vt. And let's understand here. Suppose a person traveling in a train, and the person walks on the earth. When he walks on the earth, he has a speed. He walks. Assume this person is very consistent person. He walks at his normal pace at 3 meters per second on the ground. So what we say here, we can write this. speed, but the modulus of velocity of a man with respect to ground is 3 meters per second. Direction could be anything. So he can face towards north, then his velocity in the north direction. He is walking towards east, direction may change. So whenever direction can change, the magnitude of velocity remains constant. That depends on his capacity at which his feet work and his body system work. So when he is walking on the train surface also, what is constant is velocity of man. Now he's not walking in the still ground, but to that man, it appears same as walking on the ground surface. When the train also, we are not talking about is shake and other things. You say if the man walks, is walking on the train the same way he walks on the road or the ground surface. So what will be constant now? His velocity with reference to the train surface will still be 3. Vmt will be 3. This is something is important. This comes in case of swimming also. His speed with respect to the surface he's walking on. Which surface now? Earlier it was ground, now it is train. And both the things are same. The speed remains same. Direction may change. So he is walking in the same direction as the direction of train. So what will happen? This is something, this is just moving. If this person also moves, if we observe from the ground a little later, so we are looking at taking a helicopter view, which is at rest. A little later we see it will appear like this. So train has moved a certain distance. So rear part of the train also moved certain distance. If the man was at rest, he was not moving the train, he would have moved up to this point only. But because of his velocity, this extra displacement gets added. So velocity gets added here. So what we observe here, that is as seen from the ground, that's the velocity of the man. What is the velocity of the man? Is equal to velocity of train plus velocity of man with reference to the train. So this is what happens here. So if the man in the train is observed from the ground, velocity of man is equal to. So what is ground velocity? Ground velocity is velocity of the surface plus velocity with reference to the surface. Ground velocity is velocity of the surface, which is the surface is walking on train surface, plus velocity with reference to the surface. So if train is moving, what is speed? It gets added. And this we can add in the vector form. Let's take, this is one dimension case we have taken. Let's take a 2-dimension case, something like this. And this you can observe, just imagine you're standing somewhere, you all have seen a conveyor belt. So this is like a conveyor belt, and conveyor belt is moving at a constant velocity. And this is north direction. And there's an ant walking on the conveyor belt. Suppose the conveyor belt was at rest. If the conveyor belt was rest, what will happen? This is north direction. So ant is walking consistently in the north direction. If conveyor belt was not in motion from here, it would have moved, it would have reached this point here. It would have, its ground motion would have been same because the conveyor belt was at rest. But if conveyor belt also is in a state of motion, this becomes the case of walking. So this is something, his motion doesn't change. We start moving the conveyor belt. If conveyor belt is moving the constant velocity, the ant here would not know, and keeps walking. But now conveyor belt in motion, there's additional displacement, additional velocity on account of motion of the surface. How would what would it appear like? So if conveyor belt has moved, rather than reaching here, this is where it would have reached because of its own motion. And because the surface is walking on motion, it ends up here. So this is where, if you observe from the ground, this is where the ant will end up. From here, it will end up here. And again, what is this velocity in terms of, if you vector velocity? Okay, so again, in this case, what is the ground velocity? Ground velocity is vector sum of velocity with reference to the surface plus the surface velocity. So this is velocity with reference to the surface, and this is surface velocity, which is the conveyor belt. So that becomes your ground velocity. So that is intuitive understanding of ground velocity. So if you observe from the ground, the ant will appear to be moving along the line we had drawn. This is how the motion of ant will appear like. I hope it's clear. So if belt was not in motion, so consistently what is happening? Relative to belt, it moves like this, but belt also, conveyor belt moves like this. So it will have motion continuous like this. So that's what we need to understand. And very simple point, what we need to understand here, ground velocity, and this is nothing but same expression. What is this motion here? Ground velocity is equal to relative velocity plus the velocity of the surface is walking on. That becomes VAG. And similar case, so ground velocity is vector sum of velocity with reference to the surface plus the surface velocity. And same thing applies in case of river boat. The river boat also same issue. Aeroplane, in aeroplane traveling in blowing in wind due to wind also similar case. So these are the 3-4 cases which are coming into the category of object moving on a surface which itself is under motion. Let's take a case of boat. So let's understand here. So boat also, what we understand from here. So what we say, this wordings here. Let's look and see if this part is understood. If a boat can row with a speed of 3 meters per second in still water. What is 3 meter? It depends on the propulsion system of the boat and friction and all. So in still water, I can write something like this, similar to previous case. What does this expression indicate? This expression indicates the speed of the boat with respect to the water it is rowing. But if it is showing, if it is the same boat is made to row in a river water, then so again is speed with reference to the water it is rowing upon. Relative speed still remains 3. It is similar to man walking on a surface. That's what you need to understand. This expression is velocity with reference to the surface is constant. It doesn't matter whether the surface is at rest or surface is in motion. If surface in motion, additional velocity gets added because of velocity of the surface. Its velocity with speed with reference to the surface it is swimming on remains constant. Only thing what you can change, the direction in which the way the man can walk in different direction, the boat also can be aligned in different direction. Let's see this case of boat. So this is the river here. So let's see that and how do you understand here? If the body of boat, this is something we can control the direction, not the magnitude. So if suppose the river was at rest, river was not flowing, it's like a lake. And this is not direction. If the body of boat is kept like this, what will happen? Boat will continuously move like this, and it will keep moving the speed of 3 meters per second. Now, similar to conveyor belt, what we do, we make the river. Now, this is not a lake. River start flowing. Because river start flowing, even though the boat is trying to move in this direction, with reference to river surface. Now, river also is taking it further downstream. So, actual ground motion will not be like this. Actual motion will add velocity of the river here also. That becomes the ground velocity. So that's what we need to understand here. So this is river velocity. This is velocity of boat. VBR, how do you find the direction of VBR? Magnitude is same as is speed in the still water. Direction of VBR depends on how the body of the boat is aligned. And if you are walking on a ship, so you see, if you walk in the direction facing your face, so whichever direction, if you are facing in the north direction, suppose it was a ship was moving like this. If you are facing north, you are walking velocity with reference to the ship deck is north. But if ship is moving towards east, your ground velocity will have north component as well as east component. This is something similar here. The direction as VBR is based on orientation of the boat. And this is what the kind of velocity it will end up having. This will be the ground velocity. If I observe from the shore, the boat is aligned like this, but boat will keep moving like this. And what is this one? This is again. So what is VB? Ground velocity is relative velocity to river plus the river velocity. Vector sum of the two. Ground velocity is vector sum of the two. That's why they said what is relative velocity? Vector sum, nothing else. If we draw vectors, these are the vectors. What is VB? VBR plus VR. So that's why tail of VR we keep at the head of the first vector, and the resultant vector is from the tail of the first vector to the head of the second vector. That's VB. If you can draw this vector diagram, that's all is there in relative velocity, nothing else. So this is one orientation. What will happen in that case? That's how it will end up. What happens if we change the orientation? Now it is not facing in that direction. It is facing in this direction. If I face in this direction, VBR becomes in this direction. That becomes VBR direction. VBR direction remains same, magnitude. But when we do this one, what is important here? We have changed the orientation, but length of this arrow has not changed. This length of the arrow remains same, which indicates magnitude of velocity of boat with reference to water remains constant. River speed remain constant. This ground speed will change. So depending on how VBR is oriented, how the river, how the boat is rowed, that will depend on the person rowing the boat. Depending on the orientation, this velocity will keep on changing. So by changing orientation, what we are changing? We are changing this alignment or direction of this vector. This vector remains same. Since if moment you change this vector, even though this remains constant, this also will change. So this is something like this. If we keep it like this, such that it becomes vertical. In this case, what will be the which direction the boat will move? In this case, the boat will move in a direction perpendicular to the bank, shortest path. So this is the case. We'll come to the later again. This is the minimum time orientation. This is the shortest path orientation. Okay. So general case, actual ground motion important. So what is VB? VBR plus VR, just the vector sum. Let's use the unit vector. Let's take a general case. What is VBR here? VBR is at angle theta with the y direction in anti-clockwise direction. So let's take this and this take x coordinate, y coordinate, I cap, j cap, and then express in terms of unit vector. So we are always generally interested in VB. What is the ground velocity of boat? If you express this vector plus this vector, so either I can solve using graphical method or we can use analytical method in terms of unit vector. So what is VBR equal to? What is VBR? If this angle is theta, if this angle is theta in terms of ij vector, if this angle is theta, how we measure theta? With reference to y-axis in anti-clockwise direction. If this is there, is x component is this, x component is equal to VBR sine theta. X component is minus VBR sine theta I cap plus y component is VBR cos theta j cap. That becomes VBR. Okay. And what is river velocity? VBR I cap. What is VB? VB is equal to, we add these two, VR minus VBR sine theta I cap plus VBR cos theta j cap. So this is the velocity. Let's understand here. So this is, so we find x component as well as y component. Which component of velocity is helpful in crossing the river? We have x component of velocity, y component of velocity. This is in the ground frame of reference. So if you forget everything, it is equivalent to an object having this kind of motion. If object has this kind of motion, it has x component, it has y component. What would x component result into? Jaideep, what would the effect of this component here?
So the VBR cos theta helps him cross the.
So basically this component, because see, crossing the river, if river width is W, it means to cross the river, it has to have displacement in y direction. So only the J component helps in crossing the river. This component results in what he calls in drift. It gives a displacement in x direction, and displacement in x direction is called drift. So how much distance it has been flown downstream, this is called a drift. So this x component results in drift, and this results in crossing the river. So this is the speed at which river is being crossed, y direction. And to ground velocity in y direction. So what is the ground velocity in y direction? Another way to understand. See, for y direction, river velocity cannot give any component. River velocity does not help in any manner in crossing the river. Which component helps? Only the component of VBR helps in, only VBR contributes to the y component. So if entire VBR is available, if theta is 0, it means y component of ground velocity is equal to VBR. As theta keeps increasing, the y component keeps decreasing, and it will take more time to cross the river. So when is the river crossing time minimum? When this velocity is maximum, and this velocity is maximum and cos theta is equal to 1, or VBR component, entire component cos theta. So y component of ground velocity is equal to VBR when theta is equal to 0. Time taken to cross the river is minimum. Which is the condition here? This is a condition for minimum velocity. In this case, theta is 0. Y component of VB is maximum, and y component of VB is equal to VBR. It will take minimum time to cross the river. Okay. So this is how the river will move. This is something, if you align the boat like this, that's how the boat would move. So you understand. The ground frame, this is what will happen. And this part is because of I component of velocity. And this distance is, by the time it crosses river, the displacement along x-axis is drift. It will not reach exactly the opposite point. It will end up downstream side by a distance delta x, which is drift. We'll come to drift also. The important point is, what are the important points here? Important points are, what is the time it will take to cross the river, and which position on the opposite bank it will end up with. Okay, so let's analyze those two. Okay, so again we are saying the boatman has no control. Boatman can only control direction of VBR, not its magnitude. Both cases magnitude is same. The only thing what he can change is theta. Time to cross the river. What is the time it will take to cross the river? It will be width divided by y component of VB. Y component of VB. That's the time to cross the river. Minimum time to cross the river when theta is equal to 0. We have seen earlier here. When theta is equal to 0, that's minimum time. And when theta is equal to 0, what is y component of VB? Y component is of VB is nothing but VBR. So time to cross the river is width of the river divided by VBR. Entire VBR is used for crossing. No part of VBR is having any component along x-axis. So we understand why the time is minimum. Entire boat's speed with reference to water is utilized for crossing of the river. But in this case, what will happen? We'll end up with a drift. This is a time of crossing. So during this period, boat has velocity in y direction. It also has a, what is x component of velocity of VB? In VR is the x component. And what is the drift? It will have displacement in x direction in time t. That's the drift. VR into t is the drift. So what distance downstream it will end up with? VR into t is the distance. Okay. Second part is shortest path. Shortest path is we want to reach exactly opposite point. If I want to reach exactly opposite point, means the ground velocity also should be along y direction only. It cannot have any x direct component. Then only you can reach. If you want to reach exactly opposite point, x component of boat velocity has to be 0. But since it's vector sum, how does x component become 0? When VBR and VR, their x components are equal and opposite. This entire thing is x component. So effectively, what is the condition for minimum path? X component of VBR should become equal to VR and opposite direction. It has to be anti-clockwise direction. Orientation has to boat has to be on the upstream side, not on the downstream side. So shortest path, no drift. X component velocity has to be 0. When x component of VBR cancels or negates river velocity. And what is the angle it should make in that case? It forms a right angle triangle. What is the angle theta here? We know this magnitude and this magnitude. So what is sine theta equal to? Sine theta is equal to VR by VBR. Thus, angle at which you should row to reach the opposite point. And if we row like this, what is VB value in that case? What will the ground speed of boat? Ground speed from right angle triangle, we can easily figure out. Quickly, we know these values. These are two values normally known here. If these two values are known, ground speed of VB can be found from right angle triangle. It will be equal to V bar square, VBR square minus VR square. So that is the time it will take, time to cross the river. So we notice compared to earlier, the denominator has become smaller. That's why it takes more time. So here part of the VBR is used to negate the drift. Hence the time has gone up. Okay. Now let's apply it to simple case. Let's talk, go through simple questions here. I have taken an example which has simple numbers. A boat can row at a speed of 5 meters per second in still water. Moment I read this question, this is nothing but how I should interpret velocity of boat with respect to this magnitude is 5 meters per second. That's what it implies. It is equivalent to, if you have equivalent statement in ground, I would have said a man can walk a speed of 5 meters per second on still ground, which is nothing but right road surface. If he walks on a travelator, his speed with respect to travelator surface also will be 5 meters per second. Similar statement here. It is crossing a 500 meter wide river, flowing with the speed of 3 meters per second. What is the minimum time to cross the river and the corresponding drift? What is the time to cross minimum? When is the cross timing minimum? When VBR is along y direction. This is a minimum time figure. This is how the three vectors are for crossing in the minimum time. If you understand these three vectors, rest all is pretty simple. Okay. The motion of boat in the ground frame, this is always the velocity for general value theta here. To cross in the minimum time, again, we understand this has to be maximum, cos theta has to be 1. Okay. So minimum time is equal to width of the river divided by VBR, 500 by 5. It will take 100 seconds. But during 100 seconds, what will happen? Though it is having displacement along y-axis, which is helping to cross the river, it is also being flown downstream continuously. at a speed of, what is speed it is being flown around, this term is 0. So next direction it has velocity of vr. So during 100 second, it will have a drift equal to 100 into vr. Vr is equal to 3 meter per second. It will have drift of 300 meter. So when it crosses river of width of 500 meter, the boat will not end up at exactly the opposite point. Boat will end up at a point which is on the downstream side by distance of 300 meter. That's what will happen. That's the first part. Okay, sometimes look at the second part now. We'll do multiple parts here. Part B. What is the minimum time to cross the river and come back to the starting point? Now we have two options. If I take this option, first option, what will happen? This is the starting point. I start from here. If I take shortest time path, I'll end up here. But from end up to come back here again, it becomes very difficult. I have to up the stream. It has to row up the stream and come back like this. So though if we take this path, it minimizes time to reach the opposite side, but it dramatically increases the time to come back here. So whenever we have to cross the river and come back, will not prove that point. In that case, what will happen? Minimum time will be taken when it crosses to opposite point, and from opposite point again comes back in the same manner. Then only the overall time to come back to the starting point becomes minimum. So what is minimum time to cross the river and come back to the starting point? It has to come to the starting, it must reach the opposite side. So whatever time from here, it start from S, it comes to opposite side O, and again from O it comes back to S. So what is the total time taken? Total time is, in this case, crossing the river along the shortest path twice. Crossing the river along the shortest path twice. So what is the time to cross the river along the shortest path? When we cross along the shortest path, this is my diagram. Velocity of boat has to be in the y direction. So the boat orientation has to be like this at angle theta and VR, so that they form a right angle triangle. VB along the y-axis. So I put those values. So easily arrive at this expression. So one side it will take 125 seconds. It will take 250 seconds to go and come back. Okay. Third thing, what is the time it will take to travel a distance of 500 meters along the river and come back to the starting point? So in the river, it will start from some point A here. It moves along the river to point B to 500 meters and come back. So what is the total time it will take? This is a relatively simple question. When it is moving along the river in the forward direction, its ground velocity will be sum of the two velocity. Now both the velocity in the same direction. So resultant ground velocity becomes sum of 5 plus 3, it becomes 8. So time taken for downstream journey will be equal to total distance by 8 meters per second. But when it's moving against the river, it becomes a difference of the two velocities. The downstream velocity is, river velocity is 3, and boat velocity with reference to river is 5. So net becomes 2. So time taken to return trip will be 500 by 2. Sum of these two will be total time taken to go from A to B and come back. So sometimes the question they ask also, what is the ratio of the distance to travel along the river certain distance and come back, and perpendicular to certain river and come back? So this is the question also can be put in different ways. We can solve that question also. Third question is, which direction should the bow be rowed to reach the opposite point on the bank? That question is very simple. So the angle will be like this. So in that case, what is sine theta? VBR by sine theta is VR by VBR, which is in this case, yes, from there also we can find out this angle. If it has to reach opposite point, this term has to be 0. So either you can remember this one, you can easily understand this vector diagram, or sine theta is equal to VR by VBR, which is pretty easy to find. Okay, now next question, what is the time taken to cross the river if boat direction is, sometime we can ask, if direction of boat is given, what is the time it will take to cross the river? If the angle it makes with the river direction is 120 degree, it means theta is equal to 30 degree. What is the time it will take to cross the river? All I need to do, again using this expression sine 30, I can find out, okay, in that case, this angle is given as 30. We'll find out what is the y component velocity. Y component velocity will be equal to VBR cos 30, which is equal to 2.5 root 3. So time taken will be equal to 500 divided by this expression. So any question about river boat are fairly simple. if we understand simple vector sum. What is ground velocity of boat? Relative velocity plus river velocity. We can write in terms of diagram, or we can write in terms of expression, in terms of general theta. So most questions can be solved with this. I think that's what we need to know. So I hope this everyone is, nobody has. Let's take this case here. This is also very similar. When we talk about aeroplane traveling in wind, just think of it, this also is exactly the same as boat rowing in water. In this case also, what will be the ground velocity of aeroplane? It would be its velocity with reference to wind plus with the wind velocity. Again, vector sum. And you notice this question, well, I'll quickly solve this question. And you'll notice this question is very similar to what we have done in last 5 minutes. There is a steady wind of 60 meters per second going towards east, and aeroplane can travel a speed of 100 meters per second in the still air. Okay. And let's say it has to travel along the sides of a square of side of 16 kilometers, which are along north, south, and east, west direction. So this is how the field is. This is east direction. This is north direction. Okay. So this field is oriented like this. So suppose you start from here. What the airplane has to do, it has to fly like this here, fly like this here, like this here, and like this here. Each side is 16,000 meters. Okay. So in this case, all the cases very similar to previous case. Just we have given indication also. In when the since the wind is blowing in the direction, what is the ground velocity? We have to keep in mind is ground velocity is vector sum of VAW. What is VAW? VAW orientation would be, in this case, if body of aeroplane is like this. This is the direction of velocity of aeroplane with respect to the wind. And if this is the wind direction, this will become its ground velocity. So this is how it has to be orientated, and this is how it will move. So let's calculate how much time it will take. When it is traveling towards east, both are plane velocity with reference to the wind or air and wind velocity. Both are in the same direction. It will add up. It will become 160 meters per second. So time taken. So this average speed when it is traveling from this point to this point. Now second part of the journey. So first part I calculate from A to B. What is the speed it will have, ground speed, when it is moving from B to C? See, if it has to travel in the north direction, it has to adjust an angle in such a way that x component becomes equal to wind velocity. So what is the ground speed? Only the y component. Okay. And what will the y component be equal to? This square minus this square whole square root. So this will be 100 square minus 60 square, which is 80 meters per second. So this ground velocity will be 80 meters per second. When it is moving from here to here, this is the velocity in which aeroplane is moving with reference to wind. Wind is moving in the opposite direction. It will be difference of the two. It will be 40. And when it is moving, when it has to reach here also, this is how the aeroplane has to aim at. This is how it should, this direction, it should have this orientation. Then because the wind only, it will reach point A. And again, similar to this case also, this angle theta. And if we take the velocity here, this also will be equal to same, 100 square minus 60 square whole square. That's a times average speed. So what is the total time it will take? We will just add up the time taken along the 4 different sides. This is the number we come up with. So that is something, a similarity between motion of aeroplane in a wind. So that's all we have for, I think this I'll stop here today. And if